Welcome to Momentum, Impulse, and Collisions. In this video, I will walk you through a few new vocabulary terms, a couple of new equations, and how to rearrange those equations as needed. Our first new term is momentum. Now, momentum is what Newton called the quantity of motion. So how much is something moving? We abbreviate momentum as a lowercase p, that comes from the Latin word, and we find momentum by taking the product of mass times velocity. So p is equal to m times v. And our units are just kilogram meters per second. You just squish the units for mass and velocity together. Something important to keep in mind is that momentum is a vector quantity, so it has direction. This is where the direction of our velocity is going to come in very important. Is something going forward or backward, or do we consider it a positive or a negative velocity? And remember that in an equation like this, the momentum, the p, is going to be directly proportional to the mass, and it's directly proportional to the velocity. So if mass goes up, momentum goes up. If velocity goes up, momentum goes up also. If one goes down, the other goes down, and so on. But what happens when an object changes its velocity? How does that change the momentum? Well, in this case, a change in velocity causes a change in momentum. So we have delta p, or our change in momentum, is equal to the mass times the change in velocity. Or another way to say that would be that the change in momentum, delta p, is equal to the mass times Vf minus the Vi, our change in velocity. That change in momentum is also known as something called impulse. Impulse is how much force is acting on an object and for how long is that force acting. So we can say that I, or impulse, is equal to force times delta t. So the amount of force times the change in time, or the total amount of time. But because impulse and change in momentum are exactly the same thing, you can also say that force times time is equal to mass times that change in velocity. So impulse and a change in momentum are exactly the same thing. Now, what happens to momentum when you have two objects that are involved, whether they're colliding or bouncing off each other or something like that? How does that affect the momentum? We have two types of collisions that we'll talk about. The first is elastic, and that's when two objects hit and then bounce off of each other. Then we have inelastic, where two objects hit and then they stick together and they continue traveling together. Both types of those collisions follow what we call the law of conservation of momentum. That law of conservation of momentum says in a closed system, momentum is the same before and after an impact. And there's a couple of different ways that we can show that in an equation. Basically, whatever the total momentum is before the collision is exactly the same as what the total momentum will be after. So for an elastic collision, each object has its own velocity. Let's say they bounce off of each other. Well, they're each going to be going their own speed. So we can say before the collision that the mass of the first object times its velocity plus the mass of the second object times its velocity. So in other words, the momentum of the first object plus the momentum of the second object is equal to the momentum of the first object after plus the momentum of the second object after. Okay? The mass of the first one times its new velocity plus mass of the second one times its new velocity. Let's see that in action and see what that looks like. Let's say I have two boxes that are sliding toward each other. The first box is a 6 kilogram box moving at 14 meters per second to the right. And just like we said with forces, we'll say that that's a positive direction. We have an 8 kilogram box moving at 4 meters per second to the left, so we'll call that negative 4 meters per second. Those two boxes run into each other, they bounce off, and now we have a 6 kilogram box going to the left, so we know that our velocity will be negative. And we have our 8 kilogram box that's moving at 8 meters per second to the right. So what are we actually looking for here? I want to know what is the velocity of my first box after the collision. So here's my equation that I will use. I've got it all written out for you. And we're going to solve it for V1 after the collision. I show the after with this little apostrophe to help you decide which is before and which is after. So the first thing that you're going to do is to take this momentum of object 2 after the collision. You want to move that to the other side of the equal sign. So you just subtract it. You subtract it from both sides and you end up with this second equation down here. But at that point you still aren't finished because you're solving for V1 after the collision, which means that you need to get rid of this M1 somehow. So we take the entire left side of the equation divided by M1. So your final equation for this problem is M1V1 plus M2V2 minus M2V2 after divided by M1, and that's going to give you your final answer. When you plug your numbers in, as you see down here, I'm not going to walk you through all that entire thing, you get a final answer. Negative 12 kilogram meters per second divided by 6 kilograms is equal to negative 2 meters per second. So after the collision, your 6 kilogram box is going to be traveling 2 meters per second to the left, or negative 2 meters per second. After an inelastic collision, the objects, as we said, move together, and because of that they have just a single velocity. So the momentum before is still equal to the momentum after, but in this case we have M1V1, or the momentum of object 1, plus M2V2, or the momentum of object 2, is equal to the masses of both objects times their final velocity, or the momentum of 1 plus 2. And let's see what that looks like. So I have a grandma skating toward her grandson. He's standing still because, let's say, he's not a very good skater. And grandma's coming at him. She gets to him, she slams into him and picks him up, and then they go skating off to the side all together. So what we're looking for is this velocity afterwards. I want to know how fast are they going once they collide with each other. So again, we need to rearrange our equation. And this one's pretty easy. We have the velocity right here times the combined mass. So all we have to do is just divide both sides by the combined mass so we can move it out of the way. And this is what our final equation would look like here. When you plug those numbers in, you plug in grandma's momentum plus the grandson divided by their combined mass is going to give you their velocity at the end. And when you put all those numbers in, 480 kilogram meters per second plus 0, because the grandson has no momentum when he's moving, divided by their total combined mass, which is 120 kilograms, gives you a velocity of 4 meters per second. So you can see grandma's going 6 meters per second when she's all by herself. Once she picks up the grandson, who's half her weight, she slows down just a little bit, but they do keep on moving in the same direction she was going in the first place. The last thing I want to talk about is recoil. Recoil follows the law of conservation of momentum as well. And you can see recoil when you look at something like a cannon firing a cannonball. Before the cannon is fired, the cannon and the cannonball are both at rest, so there's no momentum, it's a 0. But because momentum must be conserved, what that means is that the cannon's momentum after firing is equal to the cannonball's momentum after firing, and they're going to be going in opposite directions, which makes them equal to each other. So one cancels the other out. So we have m1 v1 after is equal to m2 v2 after. And that might look like this. Let's say I have a cannon that is 150 kilograms, a cannonball that's 5 kilograms, and after the cannon is fired, the ball is projecting at 125 meters per second. I want to know what is the recoil speed or recoil velocity of my cannon. So I rearrange my equation, and I end up with the recoil velocity is equal to m2 v2 after divided by m1. So the momentum of the cannonball divided by the mass of the cannon. And when we plug in those numbers, I get v1 after is equal to 5 kilograms times 125 meters per second divided by 150 kilograms, which gives me 4.2 meters per second after rounding to the correct significant figures. So after a cannonball, is fired, the cannonball is moving at 125 meters per second. But the cannon itself will be moving in the opposite direction at 4.2 meters per second. It's not going to just stay completely still. It's going to move backwards in the opposite direction. Just like Newton's third law says, for every action, there's an equal and opposite reaction. And that includes something like firing a cannon as well. Go on to your next video, and good luck.